So I uploaded the midterm last Thursday or Friday. So first we discuss it a little bit, just I briefly go over. And then we do practice for chapter 6.2 today, and that should be useful for doing the midterm as well. Then if we have more time, we go to the principal component analysis. So chapter 6 slides, 6.3. Okay, so at first, yeah, so this is the midterm exam. So it's similar to homework, but we have more questions, and I think the questions are more challenging than homework, at least. And yeah, so this is an exam, so work independently, but you can ask me clarifying questions. So if it is not clear what the question is asking, then yeah, you can clarify during office hours. And do all questions by using R. Yeah, so if and submit R code output and graphics in Canvas as one PDF file or MS Word file, the less than 2 megabytes and the 24 pages or less, generated by R Markdown. So in applied statistics classes, the grading is really hard. So just following the format is really important, at least for me. And also, if you consider that you work as a statistician, all outputs should be readable, otherwise the client cannot really see what it means. And sample file is available in Canvas, and if we are not successful to need a PDF or MS Word file in RStudio, they use Microsoft Word with mimicking the R Markdown format. Yeah, I think probably making MS Word is slightly easier because I don't know, but sometimes the LaTeX is required to need a PDF. But yeah. So the important thing is not to use the RStudio, but to make readable output, readable and beautiful output. And code without outputs and figures will not be graded. And late submissions will get reduced scores. Okay, so 0 to 24 hours late, the 90% of scores you will get. 24 to 40 hours late, the 70%. Actually, with this rule, I think that usually everyone submit at least the 24 hours from the deadline. And 3 questions, just be careful to follow the guideline. For example, some questions ask you to code something, so you are not allowed to use some function like the 1B. And sometimes you are allowed. So question 2 is different from 1. So in question 2, I believe that you are allowed to use the, for example, cross-validation function. And you have 3 questions, and the question 3 takes more time. So question 3 is more applied and practical question. So you actually have to find the best prediction model and calculate the cross-validated area under the curve. And so for usual, regular questions such as question 1 and 2, that you can get some simple tasks, then you get significant partial credits. But in question 3, you actually have to get the 5-fold cross-validated AUC as your prediction performance. So you have to develop the model, and actually you have to evaluate it. So it's more practical and the advanced. And in question 3, the last question G deserves more points. So question 3 is 44 points, but the significant amount of points are allocated for G. So if you only finish 1 to A to F, probably, I don't know, you will get maybe half of the scores, maybe more than a little more than half, but not much credit. So just take time to finish question 3. So other years, I ask this kind of questions, then usually students run out of time to do. So question 3 takes certainly more time. So just spend more time. Yeah. Yeah, so and the due date is next Monday. So you have, last weekend, you had the last weekend, but also the this weekend. So I hope that you can do all questions. Do you have any questions on midterm?
Seems reasonable.
Okay, great. Yeah. Okay, so today we want to do the exercise. You can find this exercise. Oh, this is exam. You can find the exercise for today under the module in Canvas. So remember that we are doing the lasso regression. I would say just lasso. And we have data set, the Avalon 1 data set and Avalon 3 data set. So Avalon 1 data set includes basically the all variables, all response, and all predictors. We have 9 predictors. And the another data set, Avalon 3, maybe we will discuss later there. Where is that? Yeah, so Avalon 3 dataset that includes the all possible predictors up to 3-way interactions and up to cubic terms. And our objective is to fit this kind of model and to find the best model. And we have so many predictors if we allow the 3-way interactions, and we have highly nonlinear models. How many predictors we have? So we have 9 predictors, coefficients, so we have 10. And then the 2-way interactions is basically 9 by 9 divided by 2. So I think that the 9 plus the n choose 9 choose 2. So probably about what, the 45 predictors and 3-way interactions. That is what, approximately n cubed divided by 6. So we have 9 predictors. So yeah, we have 81, 720, 100, yeah, maybe 150 predictors or so on. So about 200 predictors in total, I think. So out of 200 predictors, that we choose a good set of predictors to get a good prediction model. Yeah. Okay, so I will split this session into several breakout sessions, and you can discuss maybe 20 minutes, maybe 20, yeah, maybe a little more, depending on the progress. And how many students here? 1, 2, 3, 4, 5, 6, 7, 8, 9. So maybe I will split into 3 groups, maybe 1, 2. Yeah, so you can discuss how to do it. And I encourage all of you participate actively. So maybe 20 minutes, 3 breakout rooms. Okay. Maybe I move to Victoria. Okay, so 3 students each. Okay, so okay, so we open rooms.
Dr. Shinky, I guess the only question I have is I'm trying to remember where we covered the process of generating the up to three-way in a lasso. I don't remember where that was. You're muted. Thank you.
Yeah, okay, so I will type something in our session, but the all codes will be available online. And William asked me a good question, and that is how to generate the three-way interactions. So originally I included that in the exercise, but it's so complicated, so I skipped it. And so original data set is basically Avalon 1. So only the difference between original data set and the Avalon 1 is the removal of two outliers. Then I created two-way and three-way interactions. So that is a little complicated. So I put here. So the first, D is the Avalon dataset. This is almost the same as Avalon 1. Okay, so we removed just outliers.
You want us to see something?
Oh, sorry. Yeah. I was confused. Yes, I have to share the screen. Thank you.
Thank you.
Yes. Okay, so this is just for your information. So how I generated the three-way interaction datasets. And the original dataset is Avalon 1. Okay. And Avalon 1, I renamed the dataset as x1 to x9. Okay, I excluded the response variable and the remaining 9 variables as x1 to x9.
Oh, that's a lot faster way of doing it. Thank you.
Yeah, so paste x 1 to 9 separation symbol nothing. So this is within quotation nothing. So that means that we paste x1, x2, x3 up to x9. So this is the name vector for the 9 vectors. So x1 to x9. Then I generated the two-way interaction in this way. So basically this is a loop. So I is equal to 1 to 9 and j is equal to what? Sorry. And basically we have to see, for example, 1, 1 or 1, 2 or 1, 3, but j should be equal or larger than I, right? So that's why I put the j in this way. Yeah. And 1 to, I'm not sure why I excluded 2, but the I is equal to 1 to 9 and j is equal to 3 to 9. Oh, because it's a little bit the confusing part, but the x1 and x2 are both the sex m and sex f, and no way, so it does not make any sense to think about the interaction, right? So interaction between male and female is always 0. So that's why I do not allow interaction of x1, x2, and also x1 square and x2 square that do not make sense because this is binary vector.
I didn't read through the data fast enough or deep enough. How do we identify an infant in this data set?
Oh, originally we have the 3 genders, the male and the female and the infant. And that means that we need the 2 indicator variables to identify all 3 genders, right? So basically we can create the indicator variable for M and indicator variable of F and the indicator variable of I infant, but the summation of those 3 columns becomes intercept, and the intercept is already included in the model. So that means if we introduce 3 indicator variables, 1 is redundant. So that's why we only use the sex m and the sex f, 2 indicator functions.
I guess the question is for the third redundant variable, is it both yes or both no for infant?
Sorry, so the sex m is the indicator function of m, right? So and the sex f is indicator function of f. So we can say that the indicator variable for I, the infant, is the intercept minus sex m minus sex f, right? Infant,
okay, so it's so 2 nulls. Thank you.
Yeah. Okay, and this way that we can make it. Yeah, so in a simpler case, maybe I is equal to 1 to 9 and j is equal to just I and 9, right? So then we can create all interaction terms. And also that I created the name automatically by using paste function xi.j. So this makes, for example, x5.7 variable. And this is the separation symbol. So for example, we can make, if the sep equals to quotation underbar, then the resulting variable is x underbar I underbar j. So x underbar 5 underbar j or something like that. But here I just omit this. So just we put this. And if we put nothing, then I think the default is space. So it's a kind of annoying. So that's why I
So
put
you have to
this.
put it in. Okay.
Yeah. Then three-way interactions, it's slightly more complicated, but basically the same thing. So I make a loop for ijk, I is equal to 1 to 9, j is equal to I and 9, and k is equal to j to 9. But we don't have x cube or x1 cube or x3 cube. That does not make sense because it's binary, 0, 1 variable. If we take square cube, that's the same as original variable. So that's why we go from 3 to 9. But anyway, so in this way that we can create the three-way interaction variables. And I import the data, Avalon 1 and Avalon 3 again. Okay, so just I created, but I overwrite this. And Y is only in the Avalon 1 dataset. So Avalon 1 dataset is D, and Avalon 3 dataset is DA in my computer. And here is the scatter plot, so pairs D. Yeah, so it's a little bit the too many pairwise functions, but you can see that the rings is this variable, but you can see some tendency of nonlinear relationship. You can see, for example, the ridge line of this graph is not very linear. So you can see this is the length. And the length is one-dimensional quantity. So the rings is slightly a little more than one-dimensional quantity. So probably the relationship is slightly nonlinear. Okay. And maybe the weight and the rings almost linear. Maybe if we see this ridge line, I don't know. But anyway, so possible the nonlinear relationship between x1 to x9 and rings. Okay, and then, yeah, I think we don't really have enough time, so I discussed with these slides. And remember that the GLMnet function takes the matrix input. So we have to put the predictors as a matrix. So I make this as a matrix. So DA is basically x1 to x9. I think this might be more complicated if we have categorical variables with more than 2 categories, but here, actually all x1 to xn are either numeric or binary variable. So just as matrix makes sense. If we have factor variables with more than 2 categories, then you have to use the model.matrix function. Or beforehand, we have to prepare indicator functions, the hot end encoding. So the transform factor variables into indicator functions beforehand. Then, okay, so anyway, so for this data set, as matrix DA just works. This is just the number of observations by 9 matrix. We have 9 variables, so 9 matrix, 9 columns. And the format is GLMnet DAY, and alpha is equal to 1 is for lasso, I believe, right?
Yes.
Yeah, okay. And 2 is rich. No, 0 is rich, maybe.
0 is rich.
Lambda, so it does not specify anything in question B. So I just try lambda is equal to 0.01. And these are estimates. We have 192 variables, including intercept. So here intercept is 2.69. It's not penalized. And the other coefficients are penalized. And you can see many zeros. X3 coefficient is 0, X9 coefficient is 0. Maybe three-way interactions, more zeros. Generally speaking, usually, the two-way and the three-way interactions are less significant usually. So x1 to x9 most are non-zero, but the maybe x8, x3 have non-zero, zero coefficients, but the quadratic terms, cubic terms, more zeros. Yeah, if we take square root of the quadratic term, maybe the result is different, but the yeah, you can try if you'd like. But many zeros, so that is one characteristics of lasso regression. Then now we want to optimize lambda, and in lab session I tried several lambdas in exponential scale, like 0.01, 0.1, 1, 10, 100, 10,000, 1,000, 10,000. But here, I rely on the cv.glmnet function to automatically choose the lambda. So we make this function to automatically fit the model, lasso model, with different lambdas. And here is the result. And this is the log of lambda value. And the left-hand side, maybe -7. So this is the, so optimal lambda. And this is the maybe larger lambda, which isn't significantly different from the optimal lambda. But maybe logically we have to choose the optimal lambda. So here, so log of lambda is -7. So that means the exponential of -7 is the optimal point. And it depends on your computer, because the cv.glmnet function uses some random numbers. So your result may not be exactly the same as this one. I think the breakout room 1, they got the cross-validated lambda of 0.00051 or something. So it's pretty close. And actually, once you fit this model, you have already calculated mean square error, you can see with this graph. And we have to just extract that information. And that is here. So at first, we specify which lambda is the best, and I picked up the lambda. So this is the lambda which minimizes the cross-validated error in terms of the mean square error. And then we can use this, the CVM IND. So this returns the mean square error. So mean square error is the default loss function for the cv.glm function. So we can get this as 4.42. Yeah, you can do it by hand. That may be useful for midterm exam. But anyway, so you will get a similar number to this. I think the breakout room 1 got the cross-validated MSE of 4.44. So this is 4.43, so it's close. Anyway, so we have some randomness. So your answer is not exactly the same as mine. Yeah. Sometimes we set control. I'm not exactly sure. Set seed helps. Yeah, so this is basically our model performance, the mean square error of 4.43, 4.427. And EF coefficients, so we are getting coefficients. I'm not sure what's the difference between E and F. E is the count the number of parameter estimates which equals to 0 and non-zero. Okay, so you can see these are coefficients. So now that we update just this GLM model with optimal lambda. So I name the optimal lambda as BLAM. And this value is slightly different depending on your simulation. So that makes the result slightly different. And so this the coefficients, we can see of them, we can count this. So estimates equal to 0, 73, and the number of estimates, non-zero estimates, 119. So actually maybe 60% of them are non-zero. How about the breakout room 1? How many are non-zero?
I think we got 61.
51?
Either 61 or 69. I forgot which one.
For what? The zero, non-zero.
Yeah, let me see here. Actually, we got for the first, it was first asking for for non-zero, we got 69.
Non-zero 69?
Yep.
Okay, so that's much smaller than this. So yeah, so probably here 119. That's the yeah. So it depends on your simulation, but maybe roughly speaking, half of them are zeros for this one. And G just gives the baseline to evaluate model performance. So we use the three-way interactions and use lasso, so it's pretty advanced. But what if we do more basic ones? And if it's just a linear model, so LM rings on just the first order terms. So here we don't include the quadratic or cubic terms, nor the two-way interactions, three-way interactions. And we just use GLM because within the CV GLM function, the object should be GLM. GLM without specifying family option is just the same as LM. So Gaussian error is the default. So the the linear model is default. And the stepwise function, yeah, I think the breakout room 1 mentioned that we have to specify the I think the option backward. I think we are running stepwise regression and default. So maybe we should specify direction equal to backward to accurately answer the question. I just forgot to put it. And the trace 0 helps to suppress the output, so we can just hide all intermediate products. Then it's summary, and these are included predictors: the sex F, sex M, diameter, height, weight, the shaft weight, biseller weight, and shell weight. So this is deterministic process, so you should get the same answer as me. Then the cross-validated mean square error. Cross-validated mean square error is obtained by cv.glm function with, k is equal to 10 is actually default, but the tenfold cross validation. And this has some randomness, so even if the model is the same, you may have slightly different one. And my answer is 4.77. Actually, yeah, so actually, when I compiled the file before, that was 4.767. So it fluctuates. And the breakout room 1 got 4.78. So around 4.76 to 78, maybe 79. Those are correct answers. Yeah. So I will upload this to
Thank you.
After the lecture. Yeah. And take-home exam, you will use the similar techniques, so this certainly helps. But also another question that asks you to do cross-validation by hand. I mean, the cross-validation by manual code, so you are not allowed to use the cv.glm method. So that's it for today. And I think that I don't have quizzes, daily quizzes today. I think it's reasonable because you have the midterm exam.
Thank you.
Yep. Okay, so if you don't have questions, then see you on Wednesday.
Hopefully I'll have a good amount done.